Okay, so we've talked a lot about conductors and electrostatic equilibrium, and now we're going to talk about conductors that are not in equilibrium, or ones in which charges are actually flowing through. So if you connect a battery to a wire, whether it's through a light bulb or a toaster or whatever, you hook this up to something, current starts to flow. Charges are flowing through it. So this battery is pumping charges, and they then go through the circuit, whatever is in that circuit. Okay? In that case, the only way that those electrons could be moving is if there is an electric field that's pushing them. Okay, and so the idea is, where does this electric field come from, and why is it there? When we talked about electrostatic equilibrium, the electric field is zero. Well, the idea that's different than a conductor in electrostatic equilibrium is, if I look at this wire here, and I blow it up, there's a big, kind of like a pipe full of these charges. Okay, there's all these conduction electrons able to move. Okay, there's also all these fixed positive charges that can't move. And these negative charges are flowing through these, and they are having a difficult time getting through. And so they have to kind of bounce around to get through. And so there's this resistive force. And so to help them get through, you have to push them. So this battery creates a potential, which then creates an electric field throughout this wire, forcing these charges through, which go through as fast as they can, but they're resisted by the congestion inside the wire. This is a lot like drag. If I drop an object, it will fall based on the force of gravity. But eventually, if I let it fall from a high enough height, eventually it'll reach terminal speed, in which the particle or the object is moving at a constant rate, because the upward force of drag has grown to the point where it's equal to the downward force of gravity. Same thing here, is there's an electric field that is causing these charges to flow. Let's go ahead and assume that the flow is this way, okay, in this rod. And so these charges are moving like this. These negative charges are moving like that, which means the electric field should be this way. So this is our velocity, and this is our electric field. Okay? And this velocity is based on the fact that the resistive force, this drag force between the for these charged particles in this congested environment, is equal to QE, or the electric force pushing them along. And so we get a constant velocity. We call that velocity the drift velocity. And it's dependent on a few things, which I'll show in a later video. But what I want to focus on now is the fact that these charges are real objects. So if I dump 1,000 electrons in here, well, 1,000 electrons have got to make it through. Okay. Now, what's really happening is, when I have this wire, okay, I have this long wire, and if I shove 10 electrons in that end, 10 electrons come out the other end, but they're not the same 10 electrons. This wire is full of electrons. Okay, it's totally full of electrons. And what I do is I shove 10 in here, which causes this entire sea of electrons to just shift a little bit, pushing out 10 electrons that were over there. And this kind of helps us to think about the idea of how fast electricity works. When I flip on a switch, I've got a switch on the, that's my effort for a switch, and it's connected over here to a light bulb in the room. Okay, I flip that switch, and this light bulb immediately starts to glow. At least so it seems. It's so fast. Well, how does that happen? As soon as I flip that switch, I could connect a power source to this light bulb. So let's just pretend it's a big battery. Okay, and when I connect that, that basically is connecting these two wires, allowing current to flow, and immediately current can flow. But the thing is the electrons that were here take actually a heck of a long time to get over there. But this pushes this as if it's full of water, and that water immediately starts to flow. When I turn on a hose, at my house, I turn it on, and water flows out the end. Just if the hose is already full of water, water will immediately start to flow out the other end. And the same thing happens here, is the current immediately starts being pushed through that light bulb and it glows. Okay, so one thing about that really makes it important is that it's something called law of conservation of charge. In other words, if I have a pipe that breaks up, okay, and I shove 10 electrons in this end, well, 10 electrons better come out the other two ends. Now, if this pipe is bigger, maybe 6 electrons come out here and 4 electrons come out there. But whatever went in must come out because these charges are fixed. I cannot pack more in because the density is fixed. Okay? So we say, well, I in equals I out. Okay? Now, one other kind of qualitative thing that I want to do before we get into some numerics is, well, how is this electric field created? Okay? What happens is that the surface charges, there are surface charges that create the electric fields. Okay, so we get an excess of charges. So, for example, let's say the electric field is this way. Okay, in order to create that, because this thing is full of electrons, and so the inside the wire, it's neutral. There's as many electrons here as there are neutral or positive charges. Okay, and so it's neutral in here. So the only way to create an electric field is if I create surface charges. So, for example, if I have, let's say, 4 excess positive charges here, and then I drop that down to just 2 excess here, well, there's more here and less here, which causes an electric field in that direction. And then, if I drop that down to now 0 and 0, I lost 2 here, I lose 2 here, that means the electric field is going to be the same. And if the wire stays the same material and diameter, then the electric field has to stay the same. We'll see that in a little bit. And so here, if I lost 2 positive charges, and lost 2 again, I got to lose 2 again. Going from 0, losing 2 is -2. And so again, the same distance, if I lose 2 more, I get it like that. And so we get this electric field that's constant through the wire. And it's because of these surface charges. You can kind of think of them forming rings around the wire. And we already know the electric field for a ring along its axis. And that axis is pushing these charges down the pipe. So this is kind of a qualitative picture, but it's really important for us to know how do charges actually move through a wire.